So, we have been looking at goal trees and AND/OR trees, and we looked at an algorithm called AND/OR star. But AND/OR trees are used in other places also, notably in logical reasoning or logical deduction. So, let us spend a little bit of time understanding how there is a connection between logic, knowledge, representation, reasoning that I had spoken about during the introduction, and what we are studying, which is search methods for solving problems, which basically means searching for something, solutions, searching for solutions, whatever the case may be. In the case of logic, it is searching for a proof for a given statement. So, without going into the details of what is the language we use for logic. So, typically we use something called first order logic or predicate logic. We want to try and understand the role that search plays in deduction, and in particular we will look at one form of deduction called backward chaining, which has close connections with the AND/OR graphs that we have been talking about essentially. So, hopefully we will make a connection which at a later point you may have a chance to explore in more detail if you were to do a course on knowledge representation, reasoning or logic and deduction. But there is a connection in which how machines can find proofs essentially, and it is principally by search essentially. So, what is the problem in logic? That you are given a knowledge base uh, which we represent by KB. So, this is a knowledge base, and by a knowledge base we mean a set of sentences which we assume to be true or which are premises or axioms or whatever you want to call them, but we do not question them, we assume that they are true essentially. And that is shown in this shaded circle. Each square is a sentence. So, a sentence in logic, whichever logic language that we are using, but we will stick to first order logic, which is also called as predicate calculus. Whichever language you are using, a sentence in logic is something which is either true or which is false, at least in classical logics, that a sentences can only take one of these two truth values, either true or false. So, that is given to us a knowledge base, which is a set of premises or the set of axioms, and we are given some sentence which is called alpha, and we want to ask whether this sentence is also true or not. So, in logic there are two notions. One is the notion of truth, which is a semantic notion, and one is the notion of provability, which is a syntactic notion, which means a proof, for example, is a syntactic notion that if x and y are true, then z can be true. We do not use the word true. Informally we may use the word true, but more formally we say if x and y belong to the set of sentences, then z can be added to the set of sentences. And there is a hidden implication which says that if our logic is sound, it means that whenever we add a new sentence to the knowledge base, the sentence will be true. So, that is called soundness property of logic, and most logics that we work with are sound essentially. So, we have this task that given this sentence alpha and given this knowledge base KB, which as I said is a set of sentences assumed to be true or given to be true to us, is a given query sentence alpha necessarily true. This necessarily true is a notion of entailment in logic, which says that if you accept that every sentence in the knowledge base is true, then you have no choice but to accept that this alpha is true. If that happens, then we say that alpha is entailed by the knowledge base. Now, that is a semantic notion, as I said, it is a notion concerned with truth. But when you talk about proofs, we say can you generate alpha somehow from the knowledge base. So, if you have studied logic, you would have looked at rules like modus ponens and modus tollens and disjunctive syllogism and that kind of stuff. And what you were doing, if you were doing forward chaining, which is sometimes also called uh, natural inference, you would, for example, have a rule which would say that if this sentence, the, if these two sentences are true, then this sentence is also true. Then you might have another rule which says that if these two sentences are true, then this sentence is also true. Then you might have a third rule which says that if these two are true, then these two are true. So, you keep adding those sentences and this is the process of generating a proof, and eventually we might say that uh, we can add the goal sentence to that essentially. Which two sentences to pick at any given point to generate a new sentence is the subject of search. So, the Greek syllogism is what most people who study logic they start with, and that is this classical example. What is given to you are two sentences, that all men are mortal and Socrates is a man, and from this you should conclude that Socrates is mortal. And the whole idea of entailment is that if the first two sentences are true, then the third one has to be necessarily true. So, that is the notion of entailment. What we are interested in, a notion of a proof. This is known as a Socratic argument, uh, and Socrates also gave a mechanism. He gave a set of syllogisms, which are basically patterns of reasoning, and he said that this kind of pattern is a valid pattern or a sound pattern. So, we could have replaced, for example, men with cities and mortal with congested and Socrates with, let us say, Chennai or any city, since we are in Chennai here, and of course, this man would be city. So, the point about logic is that it is formal, and when we say formal, we mean that it depends upon the form of the argument. It does not mean, it has nothing to do with content. An argument is valid, it conforms to a acceptable form, and Aristotle gave us these many different syllogisms. This is one of them, and as we have seen in the example, we are saying if all men are mortal and Socrates is a man, then you should necessarily believe that Socrates is mortal. But if we replace men with cities and mortal with congested and Socrates with Chennai, then what we are saying is all cities are congested, Chennai is a city, and therefore, you have to accept that Chennai is congested. So, it really depends on the form. All x's are y's, z is a x, therefore, z is a y. That is the form of the syllogism that we have in the from Greek philosophy. In modern times, we would use the language of first order logic, and this is how we would represent those sentences. So, let us go over them one by one. The first sentence is all men are mortal essentially. In first order logic, which we do not have time to go into detail, this stands for all x. X is a variable which comes from the domain, and what we are saying, if x is a man, so this man is a predicate. Man x is true if x happens to be a man. Man x will be false if x does not happen to be a man. So, what we are saying that for every x in the domain, if x is a man, then this is an implication sign, x must be mortal. So, mortal is another predicate essentially. So, what do we mean by a predicate? Something which is true or false. So, man Socrates is true, man Suresh is true. As far as we are concerned, even man Sudeshna is true, because when we say man, we typically mean human here. But man apple is not true. If let us say apple is a particular fruit or something like that. So, apple is a class of things, but if we had a dog named Fido, for example, then man Fido would be false essentially, because Fido is not a dog, Fido is not a man, but Fido is a dog essentially. That is besides the point that even dogs are mortal, but we are not saying that. We are saying that in first order logic, this is how we would represent the first sentence, that all men are mortal. Uh, Says that if x is a man, then x is mortal, and this applies to any x from the domain. So, this for all x means that for any x in the domain. The second sentence simply says that x is Socrates is a man, and the third sentence says that if that is the case, if if for any x, if x is a man, then x is mortal, and if Socrates is a man, and therefore you should be able to show that Socrates is mortal. And there is a rule called modified modus ponens which allows you to do that. So, if you have studied logic, you would know that modus ponens looks like this, that if you have a sentence alpha and it implies beta, and if alpha is given to you, then you can infer beta. This is called as a rule of logic called modus ponens. The only thing here is that this alpha implies beta. So, this is alpha implies beta on the top, and this is alpha. So, this part is alpha implies. So, this is alpha implies beta, this is alpha. Actually, they are not the same. So, you say that this is slightly different, which is alpha prime, because this is saying Socrates is a man. In the top, you are saying all men or something like that. So, they are not identical. You can't do string matching and so on. So, there is a rule which is called modified modus ponens, which we do not have time to go into, which says that if you can somehow make this alpha prime look the same as alpha, and as you can see, we can do that by substituting x with Socrates, then you can apply this rule of modus ponens essentially. So, that is the process of logical deduction or logical reasoning, is that you have rules like this, rules like modus ponens, which are called rules of inference, or even modified modus ponens for that matter. These are called rules of inference, and these are valid forms of reasoning, which means that whenever these first two sentences are given to you, you can jolly well go and add the third sentence without any fear. And this process is called forward chaining, because you are moving from what is given to you to what you want to show to be true. And the language that I have written is called first order logic. It is also called predicate calculus, uh, because we are talking with predicates. So, man and mortal or city or congested, these are all predicates essentially. So, this would have been forward chaining, but as I said, we are interested in backward chaining, which is also sometimes called as deductive retrieval. Uh, and the interesting thing about backward chaining is that the goal need not be a specific propositions. It can, in the previous example, we said show that Socrates is mortal. In backward chaining or in deductive retrieval, we tend to think of the whole process as an extension of database, which you can call as a knowledge base. And just like in database, you can say show me an employee who earns more than X and who has been working for more than Y years or something like that. It will retrieve something for you. In deductive retrieval, also it will retrieve something for you, but in the process it may end up doing some logical inferences as well, and we will see an example in a moment. So, instead of saying that show that Socrates is mortal, we can even ask a query, as we will see, is there someone who is mortal essentially. And then deductive retrieval will first try to show that this sentence is true, and then also give you a value for that someone. So, the goal need not be a specific proposition, it can be it can have variables, formulas with variables, and that is because variables can match. Right. So, for example, the goal, if you want to say this is the goal there. So, just like we had the for all statement quantifier, we have the existential quantifier, as this is called, and this says that there exists a z such that z is mortal. So, it is called an existential quantifier, and typically in logic there are two quantifiers, the universal quantifier, which is for all, and this existential quantifier, it basically quantifies the variable. Existential quantifier says that there is something called Z, this Z maps to something in the domain, and that something must be mortal. Universal quantifier says that for everything in the domain, if X is a man, then X is a mortal. So, that was a universal statement. And in also a language that we do not have time to go into, the same goal can be written as this thing with a question mark. So, we have already said that we will use question marks for variables in a different context, but when it is in a goal, then a question mark corresponds to an existential quantifier, which means this query can be interpreted as an existential statement, and the statement is there a Z such that this is true, and what is this? This says that there exists a Z such that Z is mortal. So, it is like saying, is there an even number, or is there a number which is a prime? Then of course, you can answer yes or no, since you are talking about logical reasoning and answering queries, but you can also produce an example. You can say that yes, 7 is a prime number. So, there exists at least a number which is a prime. So, here we can ask a question, that is there someone who is mortal? So, the answer can be yes or no, which is the primary purpose of doing logical reasoning, that is this statement true or is this statement not true, and we want to basically add more new statements to our set of statements that we believe in. But it can also, in deductive retrieval, return a value for the variable that we are talking about. So, as we will see, it can give you a value for what, which is the value for Z. So, if you ask me, is there an even number? I can say yes, and then say 2 is an even number, or 4 is an even number, or 6 is an even number. Backward chaining allows you to do this. So, let us look at this example that we have been talking about, which is this men and mortality, and in this what is called as the implicit quantifier form, the same statement for all x, this thing is replaced by saying that I am, instead of saying for all x, I am saying that x is a universally quantified variable. So, I do not have to write for all in the formula, and that makes writing programs simpler. Essentially, you do not have to parse that for all x and stuff like that. So, people have done that as well. So, it is just a simple form of writing the same statement, it is a different form which makes reasoning easy for us. So, that is given to us, all men are mortal, which you should read as for all x, man x implies mortal x. Instead of only that, instead of writing for all x, we have said that x is a universal variable, and the goal says mortal Z, that is also a variable. And I kind of mentioned very quickly that if there is a variable in a goal, it should be read as existential, which means is there a Z such that this is true. So, this is what is given to us, and of course, some facts are given to us that uh, Socrates is a man, for example. So, yeah, so you in your knowledge base or in your database, you have a set of statements that A is a man, B is a man, C is a man, D is a man, and so on. And now you are asking, is there someone who is mortal? Obviously, that follows logically, because you have said that all men are mortal essentially, but how to get a proof? And we are looking at deductive retrieval, which is a backward chaining process which goes from goal towards facts, just like the goal trees that we were building. So, the process involves doing some substitution, and he says, okay, you are given these two statements, all men are mortal, all x's are mortal, if x is a man, x is mortal, and then you are saying, is there a Z? So, first thing is, you must add some clarity, and we do that by saying substitute variable x with the value variable Z. If you do that, that means wherever there were x, you write Z. So, here you write Z and here you write Z. So, that makes pattern matching simpler. Then this whole thing can be matched directly with that, and therefore, you can move to the left hand side, which is why it is called backward chaining, move in this direction and produce this new goal or sub goal, which says that show that Z is a man. And there is this process of substitution involved, which we will not go into the detail, but there is an old algorithm called the unification algorithm. So, what have we done? We have started with this goal saying that is there a Z which is mortal, and we have converted into a sub goal to a query that is there a Z which is a man. And now, as I said, that is available in your database already. These are the set of facts given to you, or the set of knowledge base given to you. So, you substitute variable Z with Plato, for example, and that is what is being done here. So, this theta is called a substitution, uh, and the substitution says that you can substitute Z with Plato, and your query gets transformed into, is it true that man Plato? This is the new goal. So, if I write it in the same notation, this is the new goal. That is Plato a man, and this goal is met trivially in the knowledge base, because in our knowledge base it is said that Plato is a man. So, now we are done with the task of showing that somebody is a mortal, and we can say yes, this statement that is there a Z which is mortal is true. Not only that, we can say Z is Plato, for example, or we can say Z is Socrates, or we can say Z is Aristotle. So, typical deductive retrieval can give you more than one answers if there is a need for doing that. Now, let us go back to mean sense analysis here a little bit. We saw that what it said was that achieve this goal G from the state S. So, first reduce the largest difference between G and S, and then go and achieve the goal G. So, when you reduce the largest difference, you will move from S to a new state called S prime, and then you achieve the goal from there essentially. And this is what mean sense analysis there, that first solve this sub goal of reducing the largest difference, and having solved that, then you solve the goal G after carrying forward whatever you did for producing that S prime essentially. And this is what something similar we will do in logic when there are more complex rules. So, our simple rule simply has the statement that all men are mortal, for all x man x implies mortal n. Here we have a rule with conjunctive antecedents. It says that, so this is the if part, and it says if this is true, then this is true. What is P, Q and R? These are just some predicates. So, we are saying that if x is a P and x is a Q, then x is a R essentially. In our standard language, we would have said for all x, P x and Q x, the whole thing implies R x. Again, as I said, we tend to use this implicit quantifier form because it is easier to write programs with. But what we are interested in is a rule which has more than one thing on the left hand side. It has got a conjunction on the left hand side, Px and Qx. How do we handle such rules? So, we must find something which is, supposing we ask a query, is it true that there is x which is an R? Then we will have to answer that by first looking for an x which is a P, and then the same x whether it is also a Q essentially. So, that is the general idea. So, a goal which matches the consequent of a rule. So, we are talking about backward chaining, right. So, this is the consequent of the rule, reduces to the goals in the antecedents of the rule. So, if you match R of x, or if you match saying that x is a R, then you must reduce it to showing that x is a P and x is a Q, and that is done in backward chaining by something called maintaining a set of goals that you want to be shown to be true. So, initially you start with the set R of x, we want to show that R of x is true, and then but to solve that we solve both P and Q. So, show that P of x is true and show that Q of x is true. which by now we are familiar with this idea, is an AND node, that to show that this goal R of x is true, show these two individual goals P of x and Q of x. The only difference between what we did with uh, that evening out example is that the sub goals in this case are connected. So, whichever x satisfies P must also be the x which satisfies Q. So, again this is the a knowledge base in what we call as a Skolomized notation. So, there is something called Skolem functions and Skolomized notation. So, for us, as far as we are concerned, this is a simple notation, implicit quantifier form that we are talking about, and we are going to ask a goal that is there a Z which is a nice toy. So, let us say nice toy is a predicate. We said R in the previous slide, let us call it nice toy now essentially. So, the goal is there a nice a Z that is a nice toy. What are the rules? Let us say there are two rules for defining nice toys. Rule number 1 says that if x is green and if x is circular, maybe the base is circular, then it is a nice toy. So, it must be green and it must have a circular base. That is rule number 1. Rule number 2 says that x must be red and it must have a square base. Let us say, it is a square, let us just call it a square, then it is a nice toy. So, there are two ways of showing that x is a nice toy. So, that this is the rules that given to us. What is our knowledge base contain? It contains some information about some objects, and these are as follows. So, properties of some named objects A, B, C, D, E. So, we are saying A is green, B is green, C is a circle or has a circular base, C is also red, D is also red, D has a square base, and E has a circular base. So, let us say we have these 5 objects A, B, C, D, E, and we know these properties, that something is green, something is circular, something is red, and so on and so forth. And is there something which satisfies our definition of a nice toy in here? What is the definition of a nice toy? That it must be either green and a circle, or it must be red and a square essentially. And we are looking at this process of backward chaining. So, we will start with this goal, that is there a nice toy, and see how we try to solve it, and this takes us naturally to this idea of a goal tree. So, this is a goal tree that we want to explore. At the root is the goal query, then we can apply two rules, rule 1 and rule 2. If you apply rule 1, then you have two sub goals, as you can see. One is that x must be green and the other is that x must be a circle. And what is drawn below this thing are actually facts in the knowledge base, which are shown in red rectangles. So, these are known facts, that D is a square, D is red, C is red, E is a circle, C is a circle, B is green, and A is green. That is given to us. But we want to find out that is this predicate nice toy true. And you can see that this is the same old AND OR tree that we have been talking about. How does depth first search operate? It starts by putting the query into the goal set. So, the way that we implement this is depth first search, which basically means that it will go down this branch first and try to see if it can be satisfied, and then eventually scan the tree from left to right in the depth first order. And in fact, the language prologue, if you use the language prologue, does exactly this, that given a knowledge base and given a query, it does depth first search over the knowledge base, and which is what we are illustrating here as well. Remember that prologue is a language I mentioned some time ago, which was devised by Kowalski, and it is an implementation of this whole idea of logic programming. And the idea of logic programming is that logical reasoning can be seen as computation. Anything that you can compute in any other language like C or Pascal or C++ or Java or Haskell can be done in logic programming as well. And he says that logical reasoning subsumes all other forms of computation. And the language they implemented was called Prolog, and what it does was depth first search, and we are illustrating that. So, what is the query we had, that is there an x which is a nice toy? So, we will go down the left branch and apply the rule 1 first, and that is what is happening here. uh, we have transformed our query to a sub query or a subset of sub goals, that is there an x which is green, and is there an is the same x also a circle. So, we find that yes, A is green. So, we substitute x with A, and then our query, the second query, which is this, becomes this, that is A a circle. But if you look at our set of circles, we find that it cannot be made to be true. So, this query fails essentially. So, it will backtrack. It has tried that x is equal to A, that whether A is a nice toy or not. It backtracks and tries come down to the second branch. What is the second branch? That B is green. So, maybe B is a nice toy. So, it does that, but now it has to show that B is a circle, because that is what the rule says, that if it is a green object, then it must be also circle essentially, and again it fails essentially. So, there is no other choices left for it to do, there is nothing else which is green. So, it backtracks and now goes to the second rule essentially. So, this is the backtrack and it has gone to the second rule and says, okay, is there something which is red and which is a square, that is the rule number 2, and tries to look for that essentially. So, it will look for red objects. First it will look at C, then it will look at D essentially. So, first it looks at C and says, okay, C is red, but is C a square? And that fails because C is not a square. And then it looks at D, okay, D is red, is D a square? And it turns out that yes, D is indeed a square. So, that goal is also solved, and then we are left with an empty goal set, which means whatever we wanted to show, we have shown, and we have shown that there exists a uh, toy which is a nice toy, and that is shown as a subtree on the right hand side, and you know that the solutions to AND OR graphs are subtrees or subgraphs, and this subgraph says that yes, D which is red and D which is a square, because of rule 2, is a nice toy. Let us go back to the motivation that we started with when we started looking at goal trees, and this was this whole idea of making an evening plan. So, the same knowledge base and the same this thing has been now written in this language Prolog. If you are familiar with Prolog, then you would recognize this immediately, and the way to read Prolog statements are as follows. For example, the fourth statement says that if this is true, that X is a restaurant. So, this is there, and then there is a and if your friend likes this particular X, which is the second part, and this is the then part, then you have a dinner plan essentially. The only thing is, in Prolog, the goal is written first, or the consequent is written first, and the antecedents are written afterwards, and a rule is represented by this symbol here. So, reading the fourth line from left to right in Prolog would say X is a dinner plan if X is a restaurant and your friend likes X. And I had mentioned at some point that languages like Prolog use uppercase for variables and lowercase for constants essentially. So, everything else in the knowledge base uses lowercase things for arguments to predicates, which means that we are talking about something which is a constant, which is not a variable, and only variables can be substituted with something else essentially. So, this is the whole thing. We had said when we constructed this AND OR tree, we said that we have an outing plan which has arguments x, y, and z. If x is an evening plan, y is a movie plan, and z is a dinner plan. Then for each of these evening plan, movie plan, and dinner plan, we had these rules that it must be an outing or a movie or a restaurant, and also that your friend must like X, and the rest of the stuff is what's given to you as facts essentially, that these are the movies, these are the outings, and so on and so forth, and what all does your friend like. So, your friend likes the beach, the friend likes the matrix, the friend likes Bhuvan Shom, friend likes Saravana Bhuvan. So, what I am trying to do here is that we started off by in some sense a planning problem, that planning an evening out. Then we said we will construct goal trees and do in goal directed reasoning. And now we are saying that this thing is something which happens naturally in a language like Prolog. And Prolog is basically an instance of logic programming language, which basically does logical reasoning for you. In particular, it does backward deduction essentially. And the reason why Prolog writes the consequence on the left hand side is because in backward reasoning you have to match a goal with something in the knowledge base. So, if you look at the first line, the goal is that do you have an outing plan, and when you go to the right hand side it says that yes, you have an outing plan, if you have an evening plan, if you have a movie plan, and if you have a dinner plan. So, it is read in the goal directed fashion, and therefore, Prolog kind of inverts the way that we write rules. The consequent is on the left hand side and the antecedents are on the right hand side. It is because you are going to be searching on consequence, because you are doing backward chaining. So, corresponding to this, uh, uh, we did not draw this explicitly, uh, but you would have a AND or tree. We did draw maybe this part of the tree, but we did not connect it to the facts. The facts are there in red rectangles below, and you can see that these are the OR choices, that if you want to talk about an outing X, you can either think of a mall or you can think of the beach essentially. So, that is an OR choice. On the top of the AND this thing we had AND choices. So, just another way of drawing the same this thing. So, as we said, backward chaining does depth first search here. So, it first will search the left subtree, then the middle subtree, and then the right subtree. Remember that there are 3 subtrees here. So, it starts with the outing plan and says that okay, you have an outing plan if you have an evening plan and a movie plan and a dinner plan. You have an evening plan if you have an outing called X and your friend likes X essentially. So far there is no constants here, but in the next line you say okay, let us consider mall as an outing. So, this theta basically says that is a substitution that you are using. If mall is an outing, does it satisfy this goal that your friend likes the mall? It so turns out, as we have seen, the friend does not like mall. So, that ends up in fail, and the algorithm backtracks and says okay, let us look for another way of doing things, and let us find another way of solving this thing. Once we have solved this X part, which is the outing, then we will solve the Y and the Z part, which is the movie and the dinner. So, next time it tries X equal to beach, and it so works that your friend likes the beach. So, this part is fine. So, you are done with the outing plan, and what remains is the movie plan Y and the plan Z. So, this is what becomes the goal set that you have to solve essentially. So, next you try the movie as the matrix, and your friend likes matrix. So, that is fine. So, now you are only left with the dinner plan to worry about, and then you try out the different options. First you try the Pizza Hut, but that fails. So, then you try the Saravana Bhavan and that succeeds, and that goal is satisfied. Your goal set has become empty. So, you have solved the problem. What is the solution? The solution is hidden in the substitution, that X must be the beach, Y must be the film matrix, and the restaurant must be Saravana Bhavan. And if you look at the AND or tree that we looked at, the solution is marked in green. So, the 3 choices are shown in with green or cyan shaded rectangles, and the fact that your friend likes them are shown in rectangles with cyan outlines essentially. But as you can see, it's a subtree of the Andor tree essentially. So, there is a close link between uh, goal trees, Andor trees, planning and logical reasoning, and in particular if you are talking about backward chaining as done in the language prologue and as we have studied earlier. All of them work in Andor trees. It is just that the language like prologue does depth first search on the Andor trees, always going down the left branch first and then trying out other options. Whereas we had generalized from here onto the fact that you may do informed search if you could associate heuristic values with intermediate nodes essentially. If you could do that, then you could use a informed search algorithm. That uh, should conclude our study of Andor graphs and goal trees, and hopefully we have also got some insight into uh, how logical deduction in logic is related to search. We only saw the connection between backward reasoning or backward chaining with goal trees, but other forms of deduction also have connections to search, but we will leave that for another day.